Tassis. If you can share screen, Konstantinos.
Hello, yeah, fine.
Elias, can you enable sheen screen? Thanks.
Oh, I'm sorry.
I should be sharing. I don't know. Can you see my screen?
Yeah, we don't see the projected version though. We see it with sidebars. Okay.
Okay. Let me try again. Okay, maybe I can share these and tell me if this works.
Yes, that looks good.
Wait, what looks good? What do you see now?
You're full screen now.
Okay, do you see my slides?
Now
Yes,
we see the slides.
Yes.
Do you see my presenter view or the full slide?
No, I see the slide view. It's good.
Okay, perfect. Let's start then. Okay. So hello everyone. My name is Tassis, and today I'd like to discuss our experiment, PASIPHAE. PASIPHAE, as you can see, is an acronym. It stands for Polar Area Stellar Imaging Polarization High Accuracy Experiment. It's a little bit contrived for a reason, and that should be obvious to anybody who has visited Crete. It's not just an acronym, but it's also a name, right? It's the name of the Minoan queen. PASIPHAE is an experiment that aims to revolutionize the way the foregrounds due to galactic interstellar dust is removed by experiments like the one that was discussed before, that seek an inflationary signature in the polarization of the CMB. And let me start by introducing the team. The collaboration extends to 4 continents and includes us here in Greece, the University of Crete, and Forth, IUCA in India, the South African Astronomical Observatories in South Africa, of course, Caltech in the US, and the University of Oslo in Norway. And these are our sponsors so far. So the main target, the aim of PASIPHAE is to address specifically the thermal dust polarization foreground of the CMB. As we all know here, polarization of the CMB probes inflation, but the early universe is not the only source of polarized microwave emission. Cold, elongated galactic dust grains align by the galactic magnetic field, and so also emit polarized microwaves with the direction of polarization perpendicular to the magnetic field. The way the dust foreground is subtracted from microwave maps so far is the following. I'm showing here the various contributions to the microwave sky. It's a busy plot, but let's focus on the 2 ingredients I care about, the CMB and the dust, right? Thermal dust emission. The galactic dust, although it's very cold, around 19 Kelvin, the mean temperature according to Planck, it's still warmer than the CMB, which is at 3 Kelvin, so it dominates the emission at higher frequencies. And so what you do so far is that you make a map of the dust sky at high frequencies. Planck used 353 gigahertz, for instance, where the dust polarization dominates. And you map and subtract, you scale, right? You model, scale, and subtract the signal from what you see at around 100 gigahertz, where the cosmic signal is expected to contribute significantly. This technique of map and subtract works well for scalar quantities, such as intensity, right? And so CMB science so far has been extremely successful despite the presence of galactic dust, which, as you can see in this map here, it extends to even high galactic latitudes. It's marked here by these bluish hues, while the CMB is in the background, the orange background. Excuse me. So this is all fine and well for scalar quantities, but it may not be so good for polarization. And it's not just because the sky the model should be different from one place to another on the sky, right? There is actually a problem which is more severe than originally thought. And it has to do with the three-dimensional structure of the ISM, the interstellar medium. As our group first pointed out in 2015, you can get a situation like the following. Two clouds lie along the line of sight. One dominates the emission at high frequencies and the other at low frequencies. And the magnetic field that permeates each cloud is not aligned, right? Then the polarization pattern rotates between these frequencies for the same line of sight, trying to trace the magnetic field of the dominant cloud in its case. This so-called line of sight LOS frequency decorrelation of the polarization pattern has been studied by several groups since, but there has not been a consensus among all these studies because the effect remained elusive and unconstrained until very recently. That is a few months ago, when we actually showed the first evidence that this effect is actually present and significant in the Planck data. The key in the identification of the effect is to know where to look for it, right? And that's where the 21 centimeter data come to the rescue. This is atomic hydrogen emission from neutral gas in our galaxy. Right? And it helps in two different ways. The first one, the atomic hydrogen spectra can be used to identify locations on the sky where the line of sight intersects more than one cloud, multiple clouds. Right? This becomes evident in this cartoon, and the reason is because the different clouds are not just physically separated, but they also are separated in velocity space. So they come up as different components in the spectrum. The second way this helps, the 21 centimeter data help, is that they can help us approximately estimate the magnetic field direction in each cloud. How? Well, high resolution atomic hydrogen spectra reveal thin linear structures that are statistically aligned with the magnetic field. So the direction of the magnetic field could be inferred indirectly from the morphology of the H1 clouds. It's not a perfect technique, doesn't work always, but it works in a statistical sense. So using this atomic hydrogen data to 21 centimeter data, we identified sightlines that were susceptible to this line of sight frequency decorrelation effect by intersecting more than one clouds with misaligned magnetic fields. These locations make up our target sample, while the sightlines that intersect only the clouds that only one cloud, right? And thus you don't expect any line of sight frequency decorrelation there, make up the control. So we have a target and a control, and this is the location of the corresponding pixels on the sky. The red pixels belong to the control and the whitish pixels to the target sample. We then go to the Planck polarization data, and for each pixel in the target and in the control sample, we compute how much the polarization direction changes between the Planck frequencies 353 and 217 gigahertz. Because the target sample pixels are selected to have a higher likelihood statistically of a large line of sight frequency decorrelation, we predict that a larger angle difference between the two frequencies for the target than for the control, right? And indeed, this is what we see. Here I show the distribution of the polarization direction change, the polarization angle change between the two frequencies, 353 and 217 in the Planck maps. And I saw it for 3 sets of pixels. All the Planck pixels of the high galactic latitude with sky with a black colors, the control pixels in blue, and the target pixels in orange. D here is the spread of these distributions. The difference in D, in spread, between the target and the control samples that you can even see by eye here, is actually statistically significant, as we showed, and is robust against how you subtract the CMB, what algorithm you use to make the maps, the noise level of the 2 sets of pixels, and whatever residual systematics. In fact, correcting for Planck residual systematics, I mean, using an updated model, right, like the SRO2, decreasing the systematics increases the significance of the effect, which is exactly what you would expect. And also, let me remind you that the selection of the target and the control samples is astrophysical in nature and agnostic to any Planck systematics, right? And not only that, but this D, the difference in the spread between the target and the control sample increases as the misalignment between the magnetic field of the cloud, shown here on the x-axis, increases, just as we predicted back in 2015. So now that we have demonstrated that this effect is visible in the Planck data, the need to find a way to account for it when cleaning the microwave maps before using them to study the early universe and do inflation got more urgent, right? And that's exactly what PASIPHAE seeks to remedy. So the same dust grains that emit polarized microwaves causing all this trouble also absorb starlight and impart polarization on the emerging light from the clouds. So we can use stars of known distances as lampposts. If we measure the polarization of many stars of different but known distance along the line of sight, then we can infer the direction of the magnetic field between them and use this information to subtract the dust foreground from the CMB polarization, including the 3-dimensional effect. And actually, this is now doable. It's possible because of Gaia, basically, right? And PASIPHAE. ESA's Gaia mission has delivered reliable parallaxes for over 1 billion stars, and PASIPHAE will deliver the necessary polarization measurements. And for the first time, we'll be able to construct a tomographic map of the galactic magnetic field direction. The PASIPHAE survey will cover the high galactic latitudes that CMB polarization experiments target. It will run concurrently from 2 sites in the Northern Hemisphere at the Skinakas Observatory here in Crete, and in the Southern Hemisphere at the South African Astronomical Observatory in Sutherland. Here are the vitals of the survey. I'm not going to go into the details, but basically we hope to cover 1,500 square degrees per year and go as far as we can with the ultimate target, whole sky. PASIPHAE will measure the polarization of several million stars in a part of the sky that is essentially unexplored in optical polarization. I'm showing here the number of stars per square degree with currently measured polarization properties as a function of galactic latitude. The high galactic latitudes, which are of interest, right, to cosmology, have been neglected. And the current state of the art is disheartening at less than 1 star per 3 square degrees, basically. The reason is because it is driven, the whole polarimetry is driven by the star formation community who care about the galactic plane where stars are forming inside molecular clouds and neglect the high galactic latitudes. But PASIPHAE will take us to at least 360 stars per square degree, a 1,000-fold improvement over the current state of the art. To achieve this, both systematic and statistical uncertainties have to be below 0.1% in polarization fraction. This is unprecedented accuracy in polarimetry, in optical polarimetry, but unless we manage to achieve this limit, we cannot do our science in these high galactic latitudes, because there is little dust, so the polarization is low. But this extreme accuracy will be achieved by wallops, two innovative wide area linear optopolarimeters designed specifically for this project. So the wallops build on the well-tested, no moving parts, low systematics technology of RoboPol that has been running here. It's installed and it's running on the Skinakas Observatory with tremendous success since 2013. And it implements basically this technology, the RoboPol technology and design in a wide field instrument so that we can do mapping. The development is currently underway of these instruments, both instruments, the south and the north, at Ayuka, India, and the commissioning is planned, is expected by the end of the year, COVID permitting. Since we are pushing the envelope of polarimetry with this program, systematic uncertainties basically is the major obstacle, right, for reaching these low polarization fractions. The last 4 years, though, we have been observing a large number of stars with RoboPol to establish stable polarimetric standards all over the targeted area of the sky that are stable down to 0.1% in polarization fraction. The list of the stars, of the standard stars, will be published actually in a few months. So having the standards, we are ready to go and achieve our goals. But while the wallops are being developed and built, we used RoboPol, which is here and now, and it's working, for a pathfinding first demonstration of the magnetic tomography technique, right, that we discussed. We picked a region of the sky where we have two clouds overlapping, but only partially. We used, again, 21 centimeter spectroscopic data to do this. So we have one region, the red circle shown here, where only one cloud along the line of sight exists. And it's this elongated cloud that you can see on the lower left panel that I call the baguette cloud, right? This elongated cloud. Can you see my cursor?
Yes, I do.
Okay. And a neighboring region, a black circle here, right? Here, that we have an overlap of this baguette cloud with this croissant-shaped cloud, right? Which is actually an intermediate velocity cloud, so it lies further away in the halo. We measured the polarization of many stars in both regions. You can see them in the upper panels, and combined them with the Gaia distances. And the results of this study you can see in the lower panels, where the line segments mark the mean polarization, the mean magnetic field direction of the clouds, foreground to the left, background to the right. The mean magnetic field direction of the foreground, elongated cloud, the baguette cloud, is consistent in both circles, right? The black and the red, and seems to follow the morphology of the cloud as expected in statistical manner. On the other hand, the mean field direction of the background croissant-shaped cloud is only recovered in the black circle, where we have the overlap, and it's significantly actually misaligned with that of the foreground cloud. The angle difference is over 60 degrees. Right? So it's a troublemaker region, in other words. Okay, so say we got the 3D map, right, of the galactic magnetic field directions. How can we use this information to help the CMB foreground subtraction? There is an obvious question that I get all the time, which is the PASIPHAE survey is a polarization survey in the optical, right? Which is induced by the absorption of the dust grains. But the CMB foreground is in emission, in the microwave. So how do we connect the absorption and the emission, right? Of course, the physics is the same. It's the same dust grains that cause both. But we can actually see that there is a robust observational correlation as well that you can see here in this plot, where the optical stellar QU parameters, the Stokes parameters, which are induced by absorption, are extremely well correlated and predictive actually of the emission Q and U that you see in the foregrounds. So what happens right now in this map and subtract scheme is that the modified blackbody model, as we heard before, is basically fitted per pixel, right, based on high frequency data. I'm talking only about the dust, the thermal dust, and extrapolated to lower frequency data, right? Well, we can instead fit a fancier model where a modified blackbody is fitted per cloud, not per pixel, using H1 maps to find the edges of clouds and scale their emissivities, right? And the magnetic field direction in each cloud as measured by PASIPHAE to set the relative values of Q and U, the Stokes parameters, that give you the polarization angle in each cloud. If you have more than one clouds along the line of sight, then you naturally add up the Stokes parameters. They have this additive property. Then one can use this model that includes the three-dimensional effects to subtract, right, the foreground. Our colleagues actually at the University of Oslo, the Commander group, are developing this method. So this is the ultimate goal, right, of PASIPHAE. All of these, though, make use of the property of dust polarization to trace the orientation of the magnetic field, right? So far, I have only talked about orientations. Well, going beyond orientation, we can actually estimate the strength of the field in each cloud as well. The first method to estimate the magnetic field strength in the interstellar medium was developed by Davis and Chandrasekhar and Fermi in the 50s independently. And the idea is the following. Think of a cloud in the interstellar medium permeated by a magnetic field, shown here with the red segments. If the magnetic field within the cloud is uniform, then the polarization map will look uniform too, right? Like the left cloud. If something perturbs the magnetic field, the polarization map will become dispersed. The larger the perturbation compared to the mean field strength, the larger the dispersion of the polarization angle map. So if we measure the dispersion of the polarization map and we know something about the cause of the perturbation, we can estimate the strength of the mean magnetic field. And this is the idea behind the Davis-Chandrasekhar Fermi method. I'll call this DCF for short. The DCF method assumes that what perturbs the magnetic field is Alfvén waves. Alfvén waves are incompressible transverse oscillations of the magnetic field lines, similar to oscillations of guitar strings, right? In the first animation here on the left, you see a standing Alfvén wave, and in the second animation on the right, you see a traveling Alfvén wave propagating parallel to the field orientation, the mean field. The blue lines correspond to the magnetic field lines, right? And the black dots are supposedly gas particles or gas fluid elements. These gas, all these fluid elements are perfectly attached, as you can see, to the field lines and oscillate both in phase. And this is exactly what DCF assumes ideal MHD, in other words, perfect flux freezing, right? And this is not a bad assumption in most cases, actually, in the interstellar medium. Because of this perfect attachment, right, of the flux freezing of the gas and the magnetic field, the kinetic energy of the gas is transformed to magnetic energy of the deformation, right? And vice versa. There is an exchange of energies, leading to basically equipartition in the end of the two types of energy, kinetic energy and magnetic energy. And this is a central assumption of the DCF method.
5 minutes.
So let's write down these assumptions as equations. We have the magnetic energy density, which contains the three terms: the energy density of the mean field, the energy density of the fluctuating field, and this cross term. The Alfvén waves are transverse, which means that fluctuation is always perpendicular to the mean field. So the cross term vanishes, right? Energy balance, on the other hand, implies equality between gas kinetic energy and magnetic field energy in the fluctuating field. By dividing both sides with the mean field square and by taking a square root, we derive this equation for the mean field. There are three quantities here to estimate: the density of the cloud, which we can get from emission lines; the turbulent velocity of the cloud, which we can get from the Doppler broadening of the spectral lines; and the fluctuating to ordered magnetic field ratio, which we can get from the dispersion of the polarization angles. And this is how things have worked up to now, with the main assumption being that the perturbations were due to Alfvén waves. That means incompressible, right? The Alfvén waves are incompressible. However, observations paint a very different picture. Compressible MHD modes also exist, like the slow mode and the fast mode that you can see here on the left and right, respectively. And even if you accept that all perturbations start out as Alfvén waves, there is a wealth of instabilities that provide mode coupling, and they make the existence of compressible modes unavoidable. Actually, observations show that the diffuse interstellar clouds are supersonic and highly compressible, which means that there is significant power in the compressible modes, which are completely neglected by the DCF method. So the compressible modes contribute both to the gas velocities as well as the fluctuating to mean ordered magnetic field ratio. So omitting them actually is not such a good approximation. And with my PhD student Rafael Skalidis here, we thought we would try to bring magnetic field strength estimation into the precision era, right, as well. And here is what we did. On the left, you can see the derivation of the DCF equations again. In brief, we have the mean field, which is perturbed. Since we consider only Alfvén waves, the cross term is 0. However, in the compressible regime, the cross term is not 0. It can actually be shown that it correlates, it is tied to the density variations. Right? It's immediately connected with the density, the compressibility, the density variations. This means that the perturbation is not perpendicular to the magnetic field. It's actually not even random, right? It likes aligning itself preferentially with the mean magnetic field. This dynamical alignment, as it's called, is a well-established feature of compressible MHD turbulence. So going back to the magnetic energy density, the 0th order term corresponds to the mean field that exists anyhow. The cross term is induced by the compressible modes, as I said, and the second term and the second order term, everything contributes to it, right? Alfvén waves and compressible modes. But we are exploring here a regime where the delta B is much smaller than the B0, than the mean field, right? In other words, consistently with observations, we assume there exists a well-defined ordered mean field, and the turbulence is subalfvénic or transalfvénic, right? Under these conditions, we can neglect, of course, the second order term and keep only the first order term. So if we do this and proceed exactly like the DCF case, we can derive an estimate of the magnetic field strength with only the only difference being that we keep the first order term, and that leads to a difference of a square root, basically. Right.
2 minutes.
Here is how our method compares against other methods when tested against simulated clouds made in MHD simulations. We used MHD simulations to consistent with observations subalfvénic to create synthetic emission line and polarization data. And we applied the various methods and compared the relative difference of the estimated magnetic field that the method gives us from the actual that the value of the magnetic field in the simulation. And this is the relative difference, is this epsilon that I saw here in the y-axis, right? As you can see, the methods are not really good enough for a precision era, right? But our method outperforms all others and achieves a mean error of just 17%, right? So, although PASIPHAE science is driven by the hunt for B modes, its impact will be actually very wide. First of all, the three-dimensional tomographic map of the galactic magnetic field direction by itself will revolutionize our ability to approach questions like what is the origin of the galactic magnetic field, or is the magnetic field dynamically important in interstellar clouds, or even what is the origin of ultra-high energy cosmic rays, right? And secondly, our polarization measurements will reveal not just the interstellar medium, but intrinsically polarized sources and high energy sources like synchrotron emitters. And of course, there's always a great potential for serendipitous discovery, right, with this novel science product. So for more information, I invite you to take a look at our white paper that is on the archive. Our polarimeters and the experiment also got recent coverage by the Nature Astronomy mission control section. You can read more about it there. And of course, you can always stay updated on our latest developments on our website, PASIPHAE.science. Be careful to include the .science, otherwise there are a billion PASIPHAE sites, right? All having to do with tourist attractions in Crete. So thank you very much.
So thank you, Konstantinos, for a very stimulating talk. Let's see, questions. Subia.
Quick question. Thanks for the very exciting talk. And this program that you outlined is really the way forward. But you say you can only do 1500 square degrees per year. So it's going to take you 20 years or more to map the sky. What is the limiting factor? Is there no way that this can be speeded up?
Well, the main limiting factor is the number of telescopes, because we have actually 2 meter class dedicated telescopes to the project. I would be very happy to discuss with anybody else who would like to contribute a 3rd telescope to install a 3rd instrument. So we are actually hunting for more partners.
Is it entirely robotic? You just have to install it and it sends you the data. Is that how it works?
Pretty much, yes. The whole survey is planned and executed automatically. Yeah.
Okay, your colleagues at IUCA should be able to help. They have such a telescope close by, close to Pune.
Well,
anyway.
it's easy to say, everybody says, well, it's a meter class telescope. There are so many out there, but nobody's willing to give you one.
I understand.
That's what I discovered.
Okay.
when it comes to the actual negotiation, right, nobody wants to give you one. Yeah. But I think that the project is exciting. I think it's necessary. Yeah. The implications are very important for cosmology, and I hope that we can expand in the future. But even in these 1500 square degrees per year, we can cover a pretty good fraction of the sky that is targeted by inflation B mode experiments, right?
Thank you and good luck.
Thank you. Elias, next question from Elias. Elias, can you unmute? You have your hand up?
Sorry. Costa, I have a naive question. Suppose you map the galaxy and you get all of this data. Is that enough to clean up the polarization measurements? What happens with other galaxies? They don't affect us?
The other galaxies are point sources. They do not really, so they would appear in this L power spectrum diagram, right? It would appear on L 10,000.
Oh, okay, it's a matter of cross-section. Then you're saying it's not important.
No.
Okay, thank you.
Thank you. One last question, Norma.
Yes, thank you. Because of the title of your talk and your presentation, I would my points are very precise. Again, we know more or less now which are the order of magnitudes, or at least the bounds on the galactic magnetic fields, and also BICEP combined with Planck, or Planck with BICEP, provided two the last release papers bounds on the primordial magnetic fields. The origin of both could be the same or different. That is not still clarified. I would like to see more about your figures, namely the bounds, the numbers, with this polarimetry you could provide. And that is the first point. And the second, I would like to see more about magnetic spectral index, whatever primordial or galactic, and BB field 2 points correlation, whatever in the power or in the space. Thank you.
Yes, of course. These are the things we are after, right? So if I understand correctly, on your first question, you are looking for the value of the field, right? Is that correct?
Yes. Yes.
Okay, that's exactly why with Rafael we undertook this project, right? Trying to.
Yes, that I understand perfectly. I mean, these are which are the numbers, the figures,
well,
the bounds, with your instruments or your facilities you could provide, because
yes,
it's
but first we
necessary
have
to have an idea of what one are targeting to see. Of course, the mechanism that is classic.
Yeah, absolutely. We have to have the data first before we estimate the field, right? Of course, but that's the point. And yes, definitely. All these are very important questions, right? And the origin of the magnetic field is a very important open question as well. Yes, I agree.
Yes, but
so thanks, Konstantinos. I'm afraid that we have to move on as we're
I
running out
would
of
like
time.
to provide to see more precise, because it is possible now with the data at hand from other experiments, all that collected, there are figures, and this is necessary to detect something or to put or to place some bounds in the when one planifies an instrument. You need to have the targets or what could be the figures expected. Otherwise, because it's not the same nano Gauss than micro Gauss and so on. So
yeah, I understand your question now. So there is a problem with the existing polarization maps that you mentioned, the Planck maps and the BICEP maps, right? And the problem is that you see integrated emission through the line of sight, and that always leads to depolarization, right? So what you see is a lower bound of the magnetic field, right? Locally, the magnetic field could be larger, but it averages out, right, because of the misalignment of the magnetic field. On this line of sights, the high galactic latitude line of sights, we have actually done this. We have, there are a couple of publications a few years back with Rafael Skalidis again, and Aristrides, and there is another one coming out soon, where we show that we can actually recover the magnetic field in each cloud individually, right? And this value, surprisingly enough, is much higher than what you would expect in this, and it's usually used in these parametric models that are used for the magnetic field of the galaxy as a whole. There are people like the Imagine collaboration, right, and others that use parametric models of the magnetic field, like Galprop, right, to do cosmic ray propagation. And those models assume a magnetic field orientation and direction, which and value, which is much smaller. The value is much smaller as you go out into the halo than what we find. So in a place, for instance, just to give you an example, in a place where the magnetic field was estimated to be of the order of 1 microgauss, right, at 1 kiloparsec, we find it 11 microgauss. So this is an order.
Konstantinos, thank you. I'm sorry I have to interrupt you.
Thank you.
Let's continue this fascinating discussion in the coffee break. And so now I think we have to move on to the final